shown. Okay. So medians and altitudes of triangles, we're going to find that they can intersect at a point as well. It has an application just like the bisectors. So median of a triangle connects. Median of a triangle is a segment. Say a segment that connects a vertex of the triangle to the midpoint of the side opposite it. So you just have to find the midpoint. You could actually find the midpoints of all three sides with the perpendicular bisector construction, and then just connect the midpoint to the vertex opposite it. Just like with the others, you only have to do two of them. You don't have to do all three. So it's the segment that connects a vertex of the triangle to the midpoint of the side opposite it. So if I were to draw a picture by eye, you could say, okay, the midpoint of this side is maybe about right there. I'm going to move it over a little bit here. If I did that great of a job by eye. How's that look? Does that look like about the midpoint? I'm not constructing it. I could. Not yet. But if I connect that over to, oh, stay there. Switch back to pen. Connect that over here. That is a median. That is a median. Okay, that's what it looks like. So somehow you just have to find the midpoint and then connect it to the vertex opposite that side. Super easy construction. But you see how the perpendicular bisector would help us find that, right? If you do a perpendicular bisector, it's going to go right through this point. It's going to, perpendicular bisector goes like this. And it's a perpendicular bisector that you use to find that. Right? Alright. So here's some properties of medians. The medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. Okay, let me erase this. Let's get rid of that. Erase this. So when we connect all the, do you guys have the picture there? I saw it. I think you're drawing that down below. You have a picture of it. Okay. So here's what this is saying. If I connected all the medians, you have to draw this in as best we can. Connected all the medians here. They intersect at a point. That point is called the centroid. This is called the centroid. But what's special about this is if I know, this is what this is saying. Man, how do we label this? I don't think it's labeled in there. Let's go ahead and see if we can label this. AP. P must be in the middle. And then A is maybe here. So AP is equal to 2/3 of AD. So this must be D over here. So here's how this works. Here's one of them. I'd have to think about how to label that. But AP, this right here, this is the longer piece. AP is equal to 2/3 of AD. So this longer piece is 2/3 of AD. Or another way to say it, guys, listen. Another way to say this is that the longer piece from, say, one vertex to the centroid, whichever is the longer piece, so I could be talking about this one right here, or this one right here, or this one right here, it's always twice the length of the shorter piece, which would be like this one right here. So if I said that this piece right here was 10, then this little red piece would be 5. It's in a 2-to-1 ratio. That's another way of saying this theorem. Or this 10 is 2/3 of the whole length. Think about that. How does 10 relate to 15, Sarah? Are you with me?
Yes.
10 So there's different ways to think about it. Okay, so 10 is 2/3 of the whole length, 15. Does that make sense? That's how they state it in the textbook. But another way to think about it is that the longer piece is twice the shorter piece. That's another way. So say, for example, this over here was 8. What would this over here have to be? 4. It's in a 2-to-1 ratio. And then 8 is 2/3 of 12. That's what the theorem is saying in the text. So you're going to be asked to apply that property of the centroid of a triangle down here. And they do have a picture down here for us. So example 1. It says P is the centroid of triangle QRS. And PT is 5. So PT is from here to here. That's 5. Find RT and RP. Well, why not find RP first? I mean, that's pretty easy.
Well, that would make RP 10.
Yes, RP would have to be 10. Why?
Because it would be half, it would be like double the small one.
That's right. Right. And then to find RT, you're just adding the two together. Right?
Yes.
So RT is equal to. All right. Notice the longer segment here, the bigger one, the RP is coming from the vertex to where it hits the center. In that triangle. Okay. So that's it. That's one of the properties. I'll show up on the quiz tomorrow too. There's a little practice in the corner. Yes.
Whenever we have these, will there ever be a decimal there?
There could be. Well, you'd have to do a little bit of algebra. I mean, if I told you this was 5.3, there you go. What if that was 5.3? What would this guy do?
That's different. That's an easy decimal.
Okay. Well, okay. What if I said it was 0.75?
See, that's the problem.
It'd be 1.5. Yeah, so you just double it. So on your calculator, you go 0.75 times 2, and we'll do it for you. And you got it. And then you add the two together. So it could be in fractions. It could be in decimals. We don't want to be afraid of fractions or decimals. All right. And every time you go eat pizza, you eat some fraction of the pizza, right? Last time I had pizza back there. Okay, there you go. That makes it easy. I don't know. I ate 1 or 2 pizzas, not like 5, 12, something large. All right.
What about the breadsticks?
The breadsticks. Don't factor in breadsticks. You're just going to confuse us. Okay. So here we go. We can do construction. Guess what we're going to start with?
Drawing!
I think I am going to show you that one. It's not in here. They actually have you construct the orthocenter using coordinate geometry, which is cool. But I think I will show you the construction, smiley face construction of the orthocenter, just so you see it. I think you should see all 4 constructions of these intersections of things in the triangle. But this one, you're going to start with drawing A. Oh, you got a square. Not yet. That comes in chapter 6. Hold that thought. Hold that. Well, we're going to. Just come back for chapter 6. So draw a triangle. It'd probably be best if it were not equilateral. That's right. Everybody try and equilateral. Okay. That's going to be the best I can do. All right. And let me go ahead and change this to black. So you got your triangle drawn? All right, so here's the deal. We're going to go through the process. There you go, that'll work. That's kind of what I need to do with mine too. But yeah. So I've tried just making the vertices bigger, bigger dot. That's kind of made my construction to be off. But the bigger the dot is, the more room you have for where you can place your compass point, right? So I'll just leave it. We can see where the vertex is here. So what we're going to do is the equivalent of the perpendicular bisector construction. So just go ahead and do a perpendicular bisector of a side. So I'm going to do that right now. Remember, stretch. Which one is that? Well, I'm going to do it right now. So you swing an arc above and below from one vertex of a side, above and below, and then you go to the other side and do the same thing. Swing an arc above and below. So you land on the vertex there. So swing an arc above and an arc below. And what I do when I'm doing the median construction is I do not draw in the perpendicular bisector, because it adds too many lines to the mix. Okay, Cameron, you might have to do different sides than that one right there. Do this side or that side? I think it'd be okay. I guess you may have drawn one too big. Yes, it does. So what I'm going to do is I'm just going to take my straight edge, and I'm not going to draw the entire line segment in here. Here's all I'm going to do. I'm going to take my pen, and I'm only, so if I were going to draw through, it would go right through there, right? I'm just going to put a little mark that shows me where the median is. That's all I need. I don't need the whole perpendicular bisector. As a matter of fact, look at where my perpendicular bisector would go through. It does not hit the vertex of the triangle. So here's where the difference is. You do your perpendicular bisector only to find the midpoint of that side. So put a little tick mark there, and that's it. So go ahead and line up your take your straight edge. You don't have to raise the arcs or anything like that. Take your straight edge, and as if you're going to draw in your perpendicular bisector, but then don't draw it in. Now, watch carefully here. Does everybody have that little tick mark? No. Okay, so no. Okay, let's give everybody another minute here. Get that little tick mark there. May not quite reach. It's okay. It looks like if they were to cross, it didn't. So it has to be bigger. But if they were to cross, so put a little tick mark right there. And then what we're going to do is connect that. So here we go. I'm going to take my ruler. Okay, let's watch this part. This is where students get confused. Okay, so here's where it differs from the perpendicular bisector. I'm going to connect this midpoint to the vertex instead of drawing the whole perpendicular bisector. And so it looks like this. My vertex is right here, and I'm just going to, and my triangle is kind of close to, just adjusting that ruler here, maybe. Adjust the ruler, right? Okay, that's pretty good. Close enough. So there, let's make my dot bigger. There's my median. Okay. But notice my median is connecting the vertex, and then you got to do one more of them. Just one more, not all three, but do one more. So I'm going to go and pick another side, no matter which one, and do the same thing here. I'm going to do another perpendicular bisector construction. Do this in just a little bit. So make an arc here, an arc over here. I'm just doing this far right side. Okay, go. An arc here. Oops, I didn't go far enough over here. An arc there. So I got to go back a few times. Back over here. Make this arc go a little longer. I think, Cameron, that was what needed to happen on that one that you just did. I think they would have intersected inside that triangle if you just made the arc a little longer. That's all. So sometimes you gotta just go back, make another arc, and then if I go over here, connect them. Okay, get it the right angle. Oh. that's going to have to do. So make my little tick mark right here, and then connect that right there to this over here. I'm connecting my midpoint to the side to the vertex opposite of that midpoint. Maybe. It's at this point that I wish I were doing this on paper like you guys. Okay, that's going to have to do. So there's my median. Just cannot get this ruler adjusted just right. So theoretically, this point right here, we'll label it M for median. But that point right there is the center of gravity of that particular triangle. And your triangle is different than mine, so you have a different center of gravity. But that's the intersection of the medians, and so you need to know how to do that construction. We'll put it all together with our little activity and performance back. So sometime this week, maybe tomorrow. So there it is. And if you were to find the third midpoint here and connect it to this vertex, it will go right through that point. So we don't need to do another one. If we'd done this on cardstock, I think it says that in there. If we'd done this on cardstock and you cut it out, you could probably take like the traditional compass that looks like mine, and you could balance it on that little compass point if our construction were accurate. Okay, cool. Let me just sweep through here. Anybody have any questions on this or need help on it? So this is called the orthocenter. So what we just did, the intersection of the medians was called the centroid of a triangle, the center of gravity. And what we're going to do next is called the orthocenter. I don't know what the application is there. Don't make it equilateral. Try to make it scalene. So please make it equilateral.
I can't do anything.
Somebody should do an equilateral, so maybe you should be the sum. But what happens with the equilateral triangles is that you will end up reset page. Maybe how about that? Perfect. Okay, so draw a triangle. It's just that you don't want to assume things that are true that aren't true with your equilateral triangle. It's just equilateral triangles are like. Well, like with the equilateral triangle, all four of these things we've constructed will all be at the same point. So that's kind of deceiving. It'll all be the same. Okay, so here. Mine's looking kind of. I gotta make mine not speak. It's just looking. Oh boy. Oh boy. Okay, we'll just stop right there. Okay, so draw your triangle. Reason it's not walking on here. Okay, so there it is. So you got your triangle drawn. You guys can draw your triangle fast. Draw a triangle. Okay, that might be big enough. So this is the smiley face construction. Smiley face construction of a perpendicular. So here's what makes it the smiley face construction, guys. We are drawing. Listen carefully. This will relate. It's all kind of connects. But what we're doing is we are creating the altitude of a triangle. So it does not necessarily correspond to the perpendicular bisector. It's just, it's a perpendicular, not necessarily a bisector. So the smiley face is the construction of the perpendicular from a point not on the line to the line. And so you put your compass point up here at the top, wherever the top is of your triangle. One of the vertices, it doesn't actually matter which vertex. Place your compass point up there. If you stretch out the compass point enough so that it's going to make a smiley face that hits it at two places. Swing an arc. Okay, so there it is. I swung an arc. That's the smiley face part of it. And then, so I swung an arc from here, hit it at 2 places, and then go down to each of these 2 places where the smile intersects the line segment as best you can. Swing an arc down here, go to the other side, and swing an arc to intersect that arc. Just barely going to intersect. And then if you take your straight edge and connect through to the vertex that we started with, you should have an altitude. So my altitude, a different color here. It's not locking on here. Okay, so my altitude is right there. Finally did. So my altitude for that triangle, the constructed altitude is that one right there. Okay. And then you got to do that for one other vertex. Mine didn't turn out so great either. But we're going to do that one more time here. So I'm going to pick maybe, it doesn't matter which one, maybe I could pick this point right here. But when I swing my smiley face, let's see here. I got all these extra marks in here, sorry. You know what might happen too, just to warn you, it's possible that when you swing your smiley face, look at this, this is a good one for me to do. It's going to hit at a spot that you would have to extend the side length to see where it hits. That's possible. Okay, think about altitudes and triangles. You know those, it's like an obtuse triangle. Think about an obtuse triangle. I'll draw it right here. Just a quick sketch for you. But in an obtuse triangle, such as this guy, where's the altitude coming off of this point going to be? It's not even in the triangle, right? That altitude is going to be right here. So you have to extend this piece out. There's my altitude from there. So that's what's happening here. Is you can have an altitude that's going to hit at a different point here. So here we go. Swing, oops. Just swing my arc right there. I need to come back over here. Back over here. I'm gonna, if I can get my ruler to line up, I've got to extend out my line segment. That's right. We're going to do it algebraically, so it's not going to matter. There it goes. So I extend this out as best I can. Mine's not locking out. But I had to extend this side length out so I could see where my other part of the smiley face hit the side of this triangle. And then from there, take and swing arcs out here. Oh, I got to change it back to solid. So swing arcs out here. And then over here, swing another arc. I know, well, that's what I'm saying. You can have, in certain triangles, an altitude that's not inside the triangle. I mean, that can happen. So if I connect this on through here, if I can get it to line up, that's close. Well, ooh, that's close. So my altitude goes like this here. And if I were to extend this one out right here, this one out right here, this would be what we call the orthocenter. But it's the intersection of all the altitudes in the triangle. Okay, so it can be constructed. I think because of these issues, we didn't ask you to construct this one. We're going to do it algebraically, which is kind of cool. I'll show you how to do that. It's a really good connection between Algebra 1 skills. You've got to be able to get the equation of a line and the geometry there. So we're going to do that next. So if you don't quite follow this, that's okay. But the idea is it's the smiley face construction because you're getting a perpendicular from a point to a line that the point's removed from, it's separate from. You draw in those altitudes, and where those altitudes intersect, this is called right here the orthocenter. Orthocenter. that reminds you of the scary ortho center. So there it is. Ortho center. Okay. An ortho center? I don't think I've ever been to an ortho center, but there's an ortho center from a triangle. All right. So, concurrencies of altitudes of triangles. So they're just claiming that the lines that contain the altitudes, here they have a picture, guys, of an obtuse triangle, all meet at a common point, and that's called the orthocenter. There's the acute triangle. There's the right triangle. The right triangle is easy because it's, maybe that's what our picture over here. Right triangle, it's the two legs that are 2 out of 3 of the altitude. So if it's a right triangle, you don't even have to construct it. You could just trace the legs or find the right angle, and that's where the orthocenter is. So that's kind of cool. On the acute triangle, this is what it looks like. The obtuse triangle, it looks like that. It's meeting outside. So pretty good sketches there. Okay, so it says find the orthocenter of triangle ABC if it has coordinates A at 1, 3. So go ahead and plot these points, please. So 1, 3, we've got A. B is at 2, 7. So B is at 2, 7 up here. Move this A over here. Oops. Need it at 1, 3. Okay, just and then the other one is at 6, 3. So I'm just going to move my A a little bit farther left here. There it is. So it's not inside the triangle. So there's A, B, and then C is at 6, 3 right here. There's C. So draw your triangle in. And here's what they're asking us to do. This is pretty cool. They're asking us to find and graph the equations of 2 of the lines that contain the altitudes and then solve a system of equations. So what we're going to be doing is finding the equation of a line, maybe from A over to BC, and it's got to hit at a right angle. So here's the deal. If I want to guarantee that a point starting right here, I'll do it in red, going over to here, I don't want to draw it in yet, I want to be accurate, hits at a right angle, what do you need to know about the slope of this line? How does the slope of the line perpendicular to BC compare? This goes back a little bit. This is what we're doing in Algebra 1 right now, like today's lesson. How do you know 2 lines are perpendicular in Algebra 1? Okay, how do you know they make it?
If you measure it.
Okay, but we're not measuring it. That's all geometric stuff. Very nice. Yeah. Yeah, slope is opposite and reciprocal. So algebraically speaking, you do know that, yes. Algebraically speaking, we know that 2 lines hit at a perpendicular at a 90. No measuring required, right? No protractor required. If their slopes are opposite reciprocal, that's pretty good. So, can I figure out the slope of BC?
Yes.
Can you figure out the slope of BC? Okay, what is the slope of BC? We go down 1, 2, 3, 4, and over 1, 2, 3, 4. It's super easy to figure out. It's not positive 1, though. It's negative 1. So M equals negative 1 for BC. And you might want to write this down so you know the process that I'm going through to get the equation of this line. And this line is going to go from point A, it's going to go from point A over to BC, but it's got to have opposite reciprocal slope of negative 1. What's the opposite reciprocal slope of negative 1?
That's 1.
No. Just 1, yeah. So I'm going to go from point A, here we go. Everybody with me. From point A, go up 1 over 1, up 1 over 1, up 1 over 1. We'll just stop right there. But if I were to draw in this line, I'll stop right there. I know that's a 90 because I used opposite reciprocal slope to draw it, right? So that is guaranteed to be my altitude from point A over to BC. If I were to continue to the left, what would I do in terms of slope? I'd go left 1 and
Down
1. Right? Left 1 and down 1, and I would eventually hit at 2. So could you write the equation of this line? It's y equals, we want mx plus b form, a little algebra review. So what is the m of this line right here? It's 1. And what's the y-intercept? I can read it right off the graph. 2. And I would write that as y equals x plus 2. So that's the equation. They're just saying you need to find the graph 2 equations. So we did one. There's one. It's y equals x plus 2, and then you can use substitution or elimination to find where they intersect. Maybe we'll be able to tell from our graph. I don't know. All right, so let's pick another point to go from. How about if I go from, well, the easy one. Here's the easy one would be this vertical line from B. I could go from C, but the easy one would be the vertical line from B. What's the equation of the vertical line from B?
Undefined.
Okay, it's an undefined slope. What's the equation? Okay, it's
Y.
right now. Let me draw this. Let me draw it. I can't remember. I know. That's what I have right now. But this is awesome because we're reviewing. Okay. Vertical line has undefined slope. I agree. That's the slope. But I'm not asking for the slope. I'm asking for the equation. So we got to think about, and I've drawn it up here. If it just goes this way, up and down, vertical, is it a y equals or an x equals line? X equals. And what is the x going to equal if I were to continue this through? 2. So I've got x equals 2 right here. So those are the 2 easiest ones. Like I said, I just kind of mentioned it. I said we might be able to just tell from the graph where the orthocenter is. Can you tell from the graph where the orthocenter is?
Yeah.
Looks like it's right here at 2, 4. Will you always be able to tell from the graph what the orthocenter is? No, that's why they suggest here that we find 2 equations and then use substitution or elimination to solve. Here's my second equation, x equals 2. So there's my system. That's my system of linear equations. What method would you use to solve this? I would too. I would use substitution because we've already solved for what? X. We already know x equals 2. How do I get y? Substitute it in, and what do I get when I substitute 2 in for x in the other equation? Does that correspond with what I thought it looked like on my graph?
Yes.
Now, if I were to find the equation from C over to AB, I would have to use the same process I did here. And guess what? It will intersect at the same point. I have to warn you, in the activity or performance task that I give you, that you might have to find 2 equations, and one of them might not be horizontal or vertical. Okay, so just be aware of that. Do we understand how I got this line from A over to BC? This is important. How did I figure out the slope of the line from A to BC? Opposite reciprocal of the line BC that it hits. Okay, and so I found the slope of BC and then took the opposite reciprocal. It was -1, which made it kind of oversimplified. But what if the slope had been -2/3? What would be the slope of the line from A to BC? If BC would be -3/2. Okay, do you see that? And then you'd have a little more work to do. That would have made it a little messier. But you could do it. You could do it. You'd find the equation of 2 of the lines that represent the altitudes, and then where they intersect is the orthocenter. So that's using what we call coordinate geometry. So in an integrated algebra and geometry course, that's the type of thing you do a lot of. So, good to know. Any questions on the orthocenter? So we've got 4 things you need to know. The intersection of the perpendicular bisectors, what's special about that point? What's it called? Or even if you don't remember what it's called, what's special about it? It is. It's the circumcenter. What's special about the circumcenter? No, it's the bigger one. It's the bigger one. So it's the bigger one that hits all the vertices. And then the second one was the intersection, right, of the angle bisectors. What's special about that guy? It's the sides. It's the in-center of the inscribed circle. I just think about all of it. But if you can at least describe what it does, that'd be good. Even if you don't remember all the vocabulary. And then the third one was what we just did today, the medians. All intersect at a point. What's special about the median? Okay, what kind of, okay, but there's different kinds of middles, right? What's that? Center of gravity if you're cut it out and balance it. And then the fourth one here was the, what do we call this? Orthocenter, and it's the intersection of the altitudes of a triangle. Okay. All right.